This video is going to be all about Newton's first law of motion, which is also called Newton's law of inertia. So we have talked about inertia previously, but let's just remember what that is, since this law is also considered the law of inertia. Oh, I lost my spot. Okay. So let me just add. Wanted to add some grid lines. Okay, so Newton's first law of motion, we are remembering what inertia is called, or what inertia is. So inertia is a property of matter that causes matter to resist changes in velocity, or we can consider that changes in state of motion. Now, I used that word velocity very specifically. So velocity, as a reminder, is a vector quantity, which means velocity has a magnitude or an amount. And it has a direction. So because objects have inertia, they are going to resist changes in the magnitude of their velocity, meaning they are going to resist speeding up or slowing down. And matter is going to resist changes in their direction of their velocity. So they're going to resist turning. So that's going to come into play later, the turning part. For now, in this unit, we're going to specifically be looking at the resisting and changes of magnitude of velocity, speeding up or slowing down. Okay. So this property of matter is based on the object's mass. Okay. If an object has more mass, then it is going to have more inertia and therefore have more resistance to changes in velocity. So if I want to speed up a toy truck, I can apply much less force than if I needed to speed up an actual truck, because the actual truck has more mass, therefore more inertia, therefore more resistance to changes in velocity. So I have to apply a greater force to get that velocity to change. So that is inertia, right? Just as a reminder. Okay. So we talked about inertia previously when we were talking about kinetic energy and why we needed to apply forces to change an object's kinetic energy. And we said we needed to apply forces because these objects have inertia. Okay. And we related that applied force to the work being done. And we ended up coming up with an equation that says the net work equals the change in kinetic energy equals FD cosine theta. So previously, up until this point, we have been looking at situations where the net work is zero because the velocity is zero, right? We are at rest. And we said, if we are at rest, then the net force in a specific direction must be zero. We were completely at rest, so we had the net force in the x direction equal to zero, and the net force in the y direction equal to zero. Now there is another situation where we can have a net work of zero, and that can be because we are at a constant velocity. So let's think of a particular scenario. Okay? So let's say we have a box, right? And I have some sort of applied force. I don't know why I did that. And that is traveling at a constant velocity. Now we already know if something is traveling at a constant velocity, there is likely some other force balancing that, friction force specifically, causing there to be no work done. So here we know the net force in the y direction is 0 because we are at rest, right? Vertically. And therefore the normal force and the force of gravity are equal. So let's think about the x direction. Now we know the net work is 0 because we are at a constant velocity, which means the change in kinetic energy is 0, right? My KE final minus my KE initial would be 0 because my initial and final speed would be the same. So my net work in a situation like this would be equal to the work done by the applied force plus any work done by the force of friction. And that would need to equal 0. So my net work would be the work done by the applied force, so FD cosine, and let's say we're moving to the right, so cosine of 0 plus the force of friction times the displacement times the cosine of 180. Okay, so my net work is FD plus a negative force of friction times D. Because the cosine of 180 is -1 and the cosine of 0 is a +1. Now I see in both of those terms a displacement, so I can factor that out. So F plus -F. Okay. So my net work looks like force minus force of friction. Now, perhaps this looks familiar to us, right? That looks like what my net force in the x direction might be, because I have the applied force minus the force of friction. Those are my only two x direction forces, and they're in opposite directions. So I can say, all right, well, my net work times the displacement times the net force equals 0. Because remember, we can carry down this equals 0 because we're traveling at a constant velocity. Now my displacement has a value. This thing is moving, right? It's not like when we were at rest and our net work was 0 because the displacement was 0. Here, my net work is not 0. It's not 0 because of the displacement, right? So that leaves us with net force. So that proves that if something is moving at a constant velocity, the net force must be 0. Okay, so that is kind of the second half of Newton's first law. The idea that the net force is 0 when something is at rest is kind of the first half, and this part is the second half. Okay, so big thing to take away here is when an object moves with constant velocity, the net force is 0 in that specific direction. Okay. So here's what Newton's first law looks like. Okay. You don't need to memorize this. You'll just see it written out. So it's usually written as an object at rest or an object moving at a constant velocity will continue to do so unless acted on by a net unbalanced force. So basically, if we are at rest or at a constant velocity, the net force has to be zero. Our forces have to be balanced. If we are not at a constant velocity, then the net force is not zero. There has to be some net unbalanced force. Now, if the at rest and the constant velocity is going to confuse you, let's remember that at rest is really just a constant velocity of zero. So really, we can simplify this statement to say an object traveling at a constant velocity will continue to do so unless acted on by a net unbalanced force. And that velocity word is there specifically, meaning we have to keep the same magnitude or same value of velocity and in the same direction. If we want to change the value of the velocity, we have to apply a force. If we want to change the direction of the velocity, we have to apply a force. So this is also called, this idea here, equilibrium, right? Which stems from the fact that the forces or opposing forces are equal, right? So if we have static equilibrium, then that triggers we're at rest. We can also have dynamic equilibrium, which means we are at a constant velocity. Okay. Now we already know how to handle questions for things at rest. We already know, or at rest. So we really also know how to handle net forces for things traveling at a constant velocity. The only thing that's going to change is the type of friction, but we will talk about that later. So let's see this in action. Okay. So we're going to go to a simulation. Okay, here. So we have this rocket sled. And currently I have friction turned off. This sled is at rest. I have a net force of 0 because my normal force and my force of gravity or weight are balanced. This sled is going to continue to remain at rest unless acted on by a net force. So if I want to get this thing moving, I need to apply a net force. So I'll apply a net force and get this thing moving a little bit. Now, if I all of a sudden stop applying a net force, my object is going to keep moving. It was moving. I stopped applying a net force, and now we're just going to continue sliding until I apply some other kind of net force to change the velocity. I could either speed it up or slow it down. Okay. So that is one way that we can have a constant velocity and a net force of 0. The other way is, let's say that there is friction, because right now in this situation, friction is currently off. So this kid's just going to keep sledding, doesn't need a force to keep him moving, just going to keep going. The net work is 0, the net force is 0, but he does have a displacement. So if I turn friction on, if I want this child to keep moving at a constant velocity with friction, I'm going to have to apply a force to balance that friction to make sure that my net force is 0. So I'll apply a force, right? I applied a force, now we're speeding up. There's my friction force. So right now, there. Now my net force is 0, right? I've perfectly balanced friction. My velocity is 12 meters a second. So now there are forces acting in that horizontal direction, the direction of motion, but the net force is 0. Right, I have a constant velocity, my net work is 0, my net force is 0, but there is a displacement. But I'm still balancing forces. So all the stuff we just worked where we were balancing boxes on free body diagrams and having net force equations of 0. That is all still true. But now we just have moving objects. Specifically, our objects are moving with a constant velocity. If I want to change that velocity, there has to be a net force. Okay. So that is Newton's first law. Okay. Let's run through a quick scenario. Okay. So let's say that I have a box, and I'm going to make it a little bit more complicated than this letter. Okay. So let's say I have a box being acted on by a force F, and let's say that force is 10 newtons, and that is at an angle of 20 degrees. Right? And let's say that the box travels at a constant velocity. Okay. So this is the effect of whatever is going on. The constant velocity is the effect, right? So maybe our first question might be, why is the box traveling at a constant velocity, right? Why are we seeing the effect that we're seeing? We're seeing the effect that we're seeing because the net force in the x direction is 0. Okay. Now you might be saying, well, Narc, why can't I say because the net work is 0? Right? Because that's another effect. We know that the net work is 0 because the net work is 0. So this statement here is the underlying cause that causes the constant velocity, that causes no work to be done, because the net force in the x direction is 0. So let's say that this is a 2 kilogram block, and we will start to solve for some stuff. Right? So let's say the first thing I want to find is the normal force. Okay. Now, vertically, this block is at rest. We can have two different kinds of motion in the x and y direction. Remember, when we are dealing with vectors, the x and y direction remain separate. So we can have two different things happening in those directions, and they are not impacted by each other. So the fact that we are at rest vertically, but traveling at a constant velocity horizontally, doesn't really matter, right? They don't impact each other. So to find the normal force, I'm going to start with a free body diagram. Okay, so here's my applied force. Here's my force of gravity. And I'm drawing this on a grid, so I'm going to draw it to scale. So I drew my applied force 2 up, and my force of gravity 1, 2, 3, 4, 5 down. So in order to show balanced forces, in order to show on my free body diagram that the net force is 0 in the y direction, I'm going to draw my normal force 3 boxes upward. That way I have a total of 5 boxes up, 5 boxes down. Right? I also know that I'm traveling at a constant velocity, so the net force in the x direction has to be 0. So I have 1, 2, 3 boxes to the right. There needs to be a force of friction, 3 boxes to the left. It's not going to be a force of static friction because this thing is not at rest. We'll talk about what kind of friction later on. Now, to help me better understand the situation and what's going on, I'm going to redraw my free body diagram, but instead of that tension force or applied force at an angle, I'm going to draw in the force components. And again, this just helps me better understand what is going on in each of the individual directions so I can draw my net force equations better. So it looks like the normal force is in the y direction. So in order to find the normal force, I need to use my net force in the y direction, right? We're at rest in the y direction, so my net force is 0. So my normal force plus my y component balance with a force of gravity. So normal force is going to be force of gravity minus my y component. So normal force is mg, that's on my reference table, minus my y component, according to my reference table, is f sine theta because I have the angle with horizontal. So if I was deriving an equation for my normal force, this would be my final answer. But I do have numbers, so I can substitute in and solve. My mass was 2 kilograms. Gravitational field strength, I will round to 10. My force is 10 newtons times the sine of my angle is 20. So 2 times 10 is 20. 10 sine 20 is 3.4. So my normal force is 16.6 newtons. All right. So then C, maybe now I need to find my friction force. Okay. Well, if I look at my net force equation, I see that the force of friction is in the x direction. So that gives me a pretty good hint that I can use the net force in the x direction. Now, yes, we are moving, but that does not mean there is a net force. We are traveling at a constant velocity. My velocity is not changing, and therefore I do not need a net force to continue traveling at that constant velocity. So my net force is 0 because we are at a constant velocity. Now again, you could consider at rest a constant velocity. It is a constant velocity of 0. Okay, so I have my x component is equal to my force of friction. According to my reference table, I can find an x component as long as I know the angle with horizontal. If I was deriving an equation for the force of friction, this would be my final answer because I have the applied force and the angle. But I'm actually solving, so I'm going to plug in some numbers. I have my 10 Newton applied force times the cosine of 20. I can do that in my calculator. And I get that the force of friction is 9.4 newtons. So again, not really much anything different from at rest. We've just expanded our definition of when the net force can be 0. Right. One more little add-on that I forgot to say. Okay. So I'm going to draw a series of free body diagrams. Okay. It doesn't really matter what the forces are. Okay. Maybe this one. This, right? So I want you to think about these free body diagrams. And I want you to think, can I tell from these free body diagrams what direction the object is moving? Okay. So pause the video and think to yourself, if these are my free body diagrams, can I tell what direction the object is moving? Okay. Hopefully you paused the video. So let's look at situation A, right? Situation A is likely an object on a table where there is a normal force and a force of gravity. Now, situation A could be an object at rest. Situation A could also be an object sliding on a frictionless surface. Object A could also be an object sliding left on a frictionless surface. Because if there's no friction, we don't need an applied force to keep us traveling at a constant velocity. We can just keep going, much like the kid on the frictionless snow. Okay? The free body diagram can't tell us the direction of motion. So let's think about situation B. So maybe situation B is, I switched the normal force and the force of gravity here. That's silly. So maybe situation B is we have two left and right forces tugging on an object. Okay. Now, without reading a question, we have no idea if situation B is at rest or traveling at a constant velocity. And we also have no idea if situation B is traveling left or right. Same with C, D, and E. Okay. So one last important thing, free body diagrams only show direction of forces, not direction of motion. Okay. Now I'm going to put a little asterisk here because there is sometimes when they can, but for the most part, free body diagrams only show direction of forces, not direction of motion, right? A, B, C, D, E, we have no way of knowing what direction these things are moving, right? D could be flying through the air at a diagonal. E could be traveling left or right. It could be a satellite out in space. We have no idea. Okay, free body diagrams only show the direction of forces, not direction of motion.